Okay. So go ahead and get these written down or take a picture, whatever you want. So we get started. There's going to be a decent amount of writing today, kind of copying notes down, and I'll explain it while y'all are doing that. So these are the basic functions. There's going to be a good amount of them you need to know. This is the linear function, y equals mx plus b, or f of x equals mx plus b. That's what a linear function is, just a line, right? This is called the identity function. I like the word parent function. It means the same thing. It just basically means it's the simplest form of it. It just y equals x. All right. You do need to know what all these general shapes look like. So make sure you have a picture of it written down, like drawn down or something like that. Of course, it's also all be on canvas anyway, but it's up to you. But you do need to be comfortable with what all the identity or parent functions look like. Or I guess the basic functions, whatever word you want to use, they all mean the same thing. Are we good here with these three? Honestly, for these, the only really important one is this last one right here. Is the only one that really matters. The one on the far right. So these are two more. The quadratic function, x squared. This is kind of what we've been playing with. We just haven't really seen it on a graph. But y equals x squared is what you need to know. And y equals x cubed is the cubic function. It'll look like this. I guess to make it a little more clear, these are all for the y equals x squared function. There's 1 point right there at 0, 0. Same thing here at 0, 0. Those are kind of important points. We'll talk about it more once we get there. But for now, just know that the basic quadratic function, y equals x squared, hits 0, 0, then goes back up. The cubic function kind of curves into 0, 0, then curves back out. Are we good there? All right. They have two more, a square root function and a cube root function. A square root function, it just starts at 0, 0, or the basic square root function starts at 0, 0, then it shoots outwards. The cube root function is just a cubic function sideways, but you kind of curve upwards to 0, 0, then curve back out at 0, 0. Are you ready to keep going, guys? Yes. Okay. Two more, absolute value function. And they call it a reciprocal function. I'm not sure why. We're going to be using the word rational. That's what the final exam review uses. That's what I'm going to use. So it's a rational function. Y equals 1 over x, and f of x equals the absolute value of x. And this goes at 0, 0 as well. This one, I wouldn't worry about this one. The rational function, I wouldn't worry about this one too much. It's a little more complicated. I think we talk about it next week or the week after, I think. So I wouldn't worry too much about this one yet. Are we good here? Anyone still copying? Need a few more minutes? Okay, we're good. Great. So now we're going to talk about some transformations of graphs. We're going to start with vertical translations and horizontal translations. They use the word translation. It's just a fancy word that means slide. So a vertical translation just means the graph can go up and down. So if you have f of x plus k, if you have this k kind of outside the function itself, like kind of by itself on the function, that means it's going up. If you have minus k right there, that means the graph is going down. Some examples can be like if we use the absolute value function, y equals the absolute value of x plus 2. What this means is that you take the y equals absolute value of x function, the one we have right here that you drew, and if you were to draw it, you draw it up to. So it would be the same exact function, except we took it and we moved it up to. And that's what a vertical translation is, or a vertical slide. All it is grabbing the function and sliding it up to, down to, whatever that number is going to be. Okay, and then f of x minus k can be something like y equals x squared minus 5. So it's going to be down 5. So you take the quadratic function and you move it down 5, and that's what a vertical shift up and down looks like. Make sense, guys? Any questions about that before I move on? Okay. So now we have horizontal translations of graphs. This one is a little tricky, so be careful. If you have something like y equals f of x minus h, so in this case, the number is right with the x, like right next to it, it's going to go to the right if it's x minus h, right? Anything that's dealing with the x is always going to be kind of the opposite than what you expect. So if you have y equals f of x minus h, you're going to the right. An example could be y equals, let's use the absolute value again, absolute value of x minus 2. This 2 is right with the x, which is different than we had before. Before, the 2 is outside, kind of away from the x, so that's why it's going up. But in this case, the 2 is right with the x, like inside the absolute value function. So in this case, you're going right to. What happens with the x is always kind of the opposite than what you expect. So y equals the absolute value of x minus 2. The graph is going right to. And then if you have x plus h, you're going to the left. So another example, if I use the quadratic, y equals x plus 2 all squared. I guess we can kind of stick with 5, so make that 5. X plus 5 all squared. Well, this is going to the left 5 because that 5 is right with the x. Compared to before when that 5 was away from the x, kind of was x squared minus 5. Well, that was x plus 5 squared. So if the number is with the x like this, it's going to be horizontally. So it's going to be to the left 5 because the x is kind of all do the opposite than what you expect. Are we fine with those? Okay. So now we have vertical shrinking and stretching of graphs. They see the word shrinking, I like compressions, but whatever it is, same thing. This is when you're multiplying the graph itself. So if your a value, so if you have like y equals a times f of x, and your a is bigger than 1, you're going to stretch the graph. An example, because I think examples kind of make more sense. If we have the absolute value function, so you have y equals 2 times the absolute value of x. So now that 2 is multiplying the absolute value, this is called a vertical stretch by 2 because it's multiplying the actual function. It's being stretched by 2. Okay?
Can you show us on the graph?
What it'll look like?
Yeah.
Sure, we can actually do it on Desmos. I think it'll be a little easier to see it. So if you have y equals the absolute value of x, this is what the basic function looks like, right? If I took that same function and let's say I stretched it, so 2 times the absolute value of x, you see how you took it, it's like it got vertically stretched, so it got a lot more narrow, right? That's what's happening. All the y's got multiplied by 2, they're twice as high. So if you look at this point right here, you see this point is negative 2, 2, the original. Well, the new one is twice as far as negative 2, 4. The y's got multiplied by 2 or it went twice as high. And that's what's happening. If it's 2, it'll be twice as high. If it was a 3, it'll be 3 times as high. Right? Negative 2, 2. Well, now you're up to negative 2, 6. We're fine with that? All right. And then a horizontal compression or shrink, whatever word you want to use, is when the A is between 0 and 1. I don't really like the definition. It's more just it's a number smaller than 1, kind of ignoring the negative. So if you have 1/2 times absolute value of x, it's going to be compressed. It's going to be a lot wider than it is tall. And there's going to be a good representation at the end what it all means when I show you. Not that. So in this case, 1/2 x is half as tall. So you had this point negative 2, 2. Well, when you compress it, that negative 2 became a negative 2, 1. The y's, because the y's are what go up and down. Those are y's are vertical. The y's are getting compressed by a half. Any questions about any of that? Are you good? Yeah.
The
The negative will do something different. That's why I don't like this definition. It really should be the absolute value of a is between 0 and 1, and the absolute value of a is 1. Because if your a is, let's say, negative 2, well, that negative 2 actually still stretches it vertically, but the negative does something different that we're going to see in a bit. So I don't like these definitions, but just always think when it comes to these numbers, the number in front of the absolute value in this case, just think of the number by itself. The negative does its own thing. So the number itself, ignore the negative. We'll stretch it if it's bigger than 1. It will compress it if it's between 0 and 1. The negative, don't worry about that. F of x just means it's the general function. It means it can stand for any function you want. The absolute value, the quadratic, the cubic, cube root, square root, whatever it is. The f of x just means any function you want, it can replace it. So in this case, f of x is the absolute value function. That's it. I wouldn't say with the word fraction. I'll stick with the word less than 0, between 0 and 1, because I can use 3 over 2. 3 over 2 is a fraction, but it's a fraction bigger than 1. It'll still stretch it. Here, right here, y equals 2 times absolute value of x. That's a stretch. Right here, that's a stretch. And this right here is a shrink. Is that what you mean? What do you mean? What? Oh, so I'm not sure I know what the question is. Stretch. So we look at Desmos. When we're talking about stretches and compressions, we're talking about stretching the original function. So y equals absolute value of x. See right there in red? That's the original function. That's the normal function. We have no other numbers around it, right? That's the original. Well, if you want to stretch it by 2, you see how the blue one, the new function, it got stretched by 2, got vertically stretched, it got taller. That's what it is. It's twice as tall. And if you use 1/2, a compression, you see how it got a lot lower, a lot got compressed, kind of a lot more narrow. Is it narrow or wider? Wider. That's what a shrink's going to be. Make sense? We're going to get there, but it's situations more like this. Is like, let's say if you want to graph it, you can use it. Or if a question I saw a few times, like if I gave you a function like y equals 2 times x minus 5 squared plus 7. If I gave you this and I told you, well, what are the transformations here? Like, how does this compare to the original parent function of y equals x squared? You'd tell me, oh, this 2 tells me we have a vertical stretch. This 5 tells me we went right 5. This 7 tells me we went up 7. So that's a question I saw on the final exam review, actually. Something similar to that, where we gave you something, we said, describe the transformations. And that's probably something how I would test you guys. Something like that. Here the equation, list out the transformations. And we'll see some examples of that in a bit. All right, any other questions, guys? Did y'all copy all this down, or anyone still copying? You good? All right. Now horizontal shrinking of graphs. I don't like this definition much either, to be honest with you. Um, but there's gonna be a kind of graphic at the end, which will kind of explain everything a little bit better than this. Uh, but it's kind of the same concept of the number that's multiplying with x is going to be doing the opposite of what you expect. So an example, if you have y equals the absolute value of 2x, like this is going to be a horizontal compression. Okay? Y equals the absolute value of 2x is a horizontal compression. And when I say it does the opposite of what you expect, well, it's 2 times x, it should make it wider, right? You'd expect that, but x's always do the opposite. So it's going to actually make it more compressed than stretched. That compresses it rather than stretches is a better way to say it. All right. And then for the next one, a horizontal stretch would be something like 1/2 x. Again, everything that's around the x always does the opposite of what you expect. So you see a 1/2 x, you expect it to be, oh, well, it actually be compressing it horizontally, but it's actually doing the opposite, it's stretching it horizontally. And I'll show you on the page in a bit, on Desmos, I mean, once you'll have this copy down. Just always know that the number in front of the x, this is going to do the opposite. You always have to flip it, kind of. Everyone done here? Or you need a little more time? You good? All right, let's go on Desmos then and see what this will look like. So the red, again, or I guess the red and the blue. No, there we go. Red. The red is the original, and the blue is the transformation one. So the blue I have 2x. That is going to be a horizontal compression. You see how it got, if you look at it from left to right, it got kind of horizontally compressed. It got pushed toward, it got a little more narrow. That's because it's a horizontal compression. Okay? And if you decide to do 1/2 x, it got horizontally stretched, it got wider, because that's what a horizontal stretch does. It will stretch it out wider, and that's what the blue one's looking like. It got stretched out wide. Any questions about any of that? The best way to think about it is really just anything that's directly with the x is always going to do the opposite of what you expect, while everything away from it kind of does what you expect it to. All right. I guess we kind of see transformations too, or translations. So you see here, if you have y equals x minus 5, it actually went to the right 5. And if we decide to do plus 2, we went to the left 2. It's always going to do kind of the opposite of what you expect. While on the outside, just kind of what you expect it to. Plus 5, let's make it plus 2. It just kind of goes straight up. Nothing happens. It's the same graph, just kind of moved up 2. And minus 2, the opposite just kind of goes down 2.
So when we do these, is the slope changing?
For the absolute value, no. Do you mean the slope for like the absolute values, right? Or what do you mean?
Just mean the slope. Like, up and down.
That's for lines. It kind of works for absolute values, but if you're not really taught that way, I'm not going to worry about it. But slope only works with y equals mx plus b. Because you have something like a quadratic y equals x squared that doesn't have a slope anymore. There's a different way to graph it. Are we good here, guys? Any questions? All right. Now we have reflections across the x and y axis. So if you have a y equals negative f of x. So as an example, y equals negative, let's say absolute value of x. That's a reflection across the x-axis. I like to think of it as a vertical reflection. Because that negative is in the same place that the vertical stretch was at. And when I wrap it all up in a bit, you kind of see what I'm talking about. Why I like to call it a vertical reflection. But that negative right there is a vertical reflection. And then the next one, you have a reflection across the y-axis. You have something like y equals the absolute value of negative x, where that's going to be a horizontal reflection. Across the y-axis is a horizontal reflection. Ready to keep going, guys? You also copying? All right. So let's go ahead and look at this on decimals as well. So the red one's going to be my original function. If I was to flip it vertically, so negative in front of it, see how the blue one just kind of flips upside down? It's just the same thing. It's a vertical reflection, reflects vertically across the x-axis. And the absolute value is not, you're not really going to see if I would put a negative in front. I'm going to change the function to a cubic. So for a cubic function, so you can actually see what's happening. If it's a reflection horizontally, like that, the blue one is the new function. You kind of see how it reflected across. Or is that kind of hard to see because it's kind of next to each other? Right, the blue one got reflected horizontally. And that's what's happening. Any questions about any of the transformations or anything like that? Are we good? What does it look like? The cubic? Well, because every number is getting cubed, and because how it is, the further you are from one, like one outwards, it grows faster. That's why it kind of curves inwards. It's just kind of the properties of numbers and how cubics work. All right. So now we have this right here. This is going to kind of wrap up everything we just talked about, I think, pretty nicely. So this is your general equation of any type of transformation on the graph, depending on where it's at. It looks like a lot, but it does kind of summarize everything we just talked about in one picture. So g of x equals a times f of 1 over b, x minus h, all plus k. And I'm about to label everything what each variable does. Okay? So the a term, which is right in front of the f of x, that's going to be vertical stretches and compressions. Or shrinks, whatever word you want to use, means the same thing. I call it compressions, but vertical stretches and compressions, or vertical stretches and shrinks, it means the same thing. That's what the number in front of the whole function will tell you. And it also tells you reflections over the x-axis. This is the vertical reflections. And that's why I like to use the word vertical here, because the number in front of the function itself does everything vertically. Vertical stretches, vertical shrinks or compressions, vertical reflections. Okay? For the b value, the 1 over b value, that 1 over b, or what's multiplying the x, does everything horizontally. So horizontal stretch and compression. And also reflections over the y-axis or horizontal reflections. Your H is just shifts or translations left and right. And K's are shifts up and down. This might look like a lot, but I promise you it's a lot better than whatever the book was giving you. I think the book had like 3 or 4 slides of like tables and stuff to try and generalize all this. I think it's a little nicer, kind of puts it all in one picture and tells you exactly where, no matter what position a number is, it does this exact thing. Okay? Are we ready to keep going, guys? Or are you also copying? Still copying? Okay. Are we good here, guys? Are you also copying? Anyone want a few more minutes? No? Okay. Now, this kind of generalized way of all these transformations to kind of understand, well, depending on where the number is, that will tell you what the transformation is. So g of x equals f of x plus 2. So what I like to do is I like to actually compare it to this graph, right? This kind of graphic right here. The 2 is in the position of that k, right? Away from the x value. That tells me it's going to move it up or down. So if you have f of x plus 2, that's telling me that we're going up 2. And that's kind of how you can kind of know, well, what is my transformation really going to be? An example of this, of what does it look like in an actual function, could be something like, I don't know, y equals x squared plus 2. That's an example of what it looks like in an actual function where the k value, the 2, is away from the x and it's doing its own thing. That is a translation up to. The red is going to be kind of an example on an actual function rather than f of x, which is kind of a general function. Everyone with me? All right. The next one, f of x plus 2. That tells me it's going to be left 2. If you compare it to the function right here, I'm adding to the x directly. So it's going to be an h value. And remember, anything with the x is always going to do the opposite of what you expect. You see a plus 2, you'd think, oh, that should be right 2 because I'm adding. Well, it's actually the opposite, left 2. Okay? If it's directly with the x, it's going to do the opposite. An example in a function could be something like y equals x plus 2 to the third power. Right? X plus 2 cubed. The 2 is directly with the x. That's why it's going to go left 2 rather than up 2. And that's the difference between going up and down or left and right. If it's up and down, it's away from the x completely. But if it's going left and right, it's directly with the x before you apply the cubic or the square or whatever it's going to be. Make sense? Any questions before I keep going? All right. Now we have a negative f of x. Well, that negative is in the place of the a value that we have. right? It's in the place of this A. So your A does everything vertically. It's going to be a vertical reflection or reflection over the x-axis. And an example in a function could be something like y equals negative, let's say, square root of x, right? It's a negative, it's a multiplying the function itself, but not the x. And then you have g of x equals 2 times f of x. Well, that 2 is still in the position of the a. Remember your a, what it does, it vertically stretches stuff. So this is a vertical stretch of 2. An example could be y equals 2 times, let's say, the absolute value of x. That's what it'll look like on an actual function. So y equals 2 times absolute value of x. The next one, g of x equals f times 1/2 of x. Well, that's multiplying the x, so it's multiplying the x itself. If you compare it to what we have here, that's the 1 over b, right? 1 over b is multiplying the x here. So it's going to be a multiplication. And remember, anything with the x always does the opposite. If it's 1/2, you think, well, it's going to compress by a half. Well, it's going to do the opposite. It's going to be a horizontal stretch. And it's going to be a stretch by flipping the number 1/2 to 2 over 1. So just 2. And an example here could be something like y equals, let's say, 1/2 x all squared. Next one, f of x minus 2. That minus 2 will tells me we're going down 2. It's the same place as that k. An example could be something like y equals x squared minus 2. Right? You're subtracting the whole function, not the x itself, but the function itself. X squared minus 2. You have f of x minus 2. That 2 is directly with the x. So it's directly with the x. It's going to do the opposite of what you expect. So it's subtracting by 2. So you think left, but it's really going to be right 2. You go in right 2. An example could be something like y equals x minus 2 all cubed. The negative x, well, the negative is multiplying the x, so that's going to be a horizontal reflection or reflection over y. An example can be y equals, let's make it the square root of negative x. That's what a reflection over the y-axis is. The negative is directly with the x, so it reflects over the y-axis or a horizontal reflection. Then you have y equals f of 2x. Again, that 2 is multiplying the x, is going to do the opposite of what you expect. So it's a horizontal compression or shrink. We'll use the word shrink because that's what they're using. By 1/2. I know it's 1/2 because you take the number and you flip it. An example could be y equals the absolute value of 2x. And then the last one, 1/2 of f of x. That's in the place of the a. It's a vertical shrink by 1/2. An example could be something like y equals uh, 1/2 x squared. Any questions about any of this? Are we good here? You can take a picture if you want or copy down whatever you like. We good? Okay. Now we're going to see how we can actually graph it, I guess. So use the transformations to graph the function defined by 2 times x plus 1 plus 3. And the parent function is f of x equals absolute value of x. And that's what we have on the left. Right, the left function is f of x equals absolute value of x. Um, I guess kind of the easiest way to graph these, to be honest with you, is knowing your h value and your k value. Your h value is always what's the opposite sign in here, with it's adding the x. So in this case, it's -1. And your k value is what's outside, is 3. So -1, +3 is a point on the graph. I say graph the hk because that's always going to be kind of the center of your graph. And in the case of the parent function, your hk is that 0, 0. That's why I kept pointing out the 0, 0 for all those parent functions before, because the 0, 0 is kind of like your hk. It's the center of the whole thing. So always start by figuring out, well, what is my hk value? And you have a point of h comma k. So in this case, -1, 3 is a point. And then from here, just honestly just plug in x and y values on both sides of that -1. That's all I would do. Just figure out the center of the whole thing, and then just plug in points. So maybe we can plug in -2 and 0 and see what we get. If you plug in -2 here, what you have is 2 times the absolute value. I guess we can do it on the side, actually. 2 times -2 plus 1, all plus 3. Or 2 times -2 plus 1 is -1, plus 3. And the absolute value of -1 is just 1. So you have 2 times 1 plus 3, or 5. So all I did was pick points to the left, because this is the center, right? That green point's the center. Yeah, so the HK point, right? So do you get how we got H and K? So that's the center of the whole graph, right? You see here in the parent function is like x plus 0, all plus 0 here, right? So 0, 0 for the regular function is the center of the whole graph. So your HK is the center of your new graph. So because you have your center, I just say, we'll pick 1 point to the left, 1 point to the right. So it's -1, so I said, well, if I have -1, let me use -2 and 0. So there's nothing special about -2, it's just a point to the left of it. Because if you have the center, you kind of want to know what's happening on both sides, right? So I just picked any point to the left of it and any point to the right of it.
So the first point would be 1, 1, and -1, or 1 negative.
So 1, 1, and -1, 1, right? Those are the 2 points for the parent function, right? But I'm trying to graph the transformation of it, right? So what I'm doing here is I'm picking points on both sides of the center, right? Because if you want to graph something, you kind of want the middle of it, something to the left and something to the right, to kind of understand, well, how is it going to look? Kind of make sense? Well, because the graph has two sides, right? The left side and the right side, right? If you have the center of it, you have a left side and a right side. Well, I just want a point on the left side and a point on the right side. That's all I want. So if you have the x value of -2, I can plug it in and I get a point -2,5. So you have a point -2,5. This is a point on the graph. Does that kind of make more sense? What I'm trying to figure out is, well, what does it look like to the left side? What does it look like to the right side? Because once you have points, you kind of just connect the dots. Make more sense? And then for 0, do the same thing. Plug that in. 2 times 0 plus 1, all plus 3. Or 2 times the absolute value of 1 plus 3. Well, absolute value of 1 is just 1, so you just have 2 plus 3, or also 5. Say the point 0.05, and that's what it's going to look like. So the absolute value, because it's just straight lines and you have your 2 points, just kind of connect the lines as straight lines and you have your answer. Yes.
If that x h end up being plus.
Yes, exactly. Everything with the x is always going to be kind of the opposite of what you expect.
Even with the absolute.
No, if it's when I say with the x, that means inside with the absolute value bars. Like it's kind of like with the function itself, right? In this case, the absolute value is with the function, so it's inside of it. If it was a quadratic, like y equals x minus 1 squared, see how the 1 is inside the function of the square? It's going to be positive 1 here. Any other questions, guys? Ready to keep going? Sure. Good. All right. And now this is a good example of something I would probably do and give y'all, where I'm going to say, well, list the transformations here. All right, so I'm going to list the transformations. So kind of what you want to do is kind of just, well, see what do we have. I have a -3, right? So I have a -3. That negative tells me we have a vertical reflection, or I guess we shouldn't use the word vertical reflection, but rather reflection over the x-axis. The actual 3 tells me it's a vertical stretch by 3. By 3 of 3, I don't think. It's a math class, not an English class. I don't care. As long as I know what you mean. Right? So vertical stretch of 3 by 3, whatever. I have an x minus 2 here. That minus 2, remember, always is the opposite. So instead of a left 2 that you'll think, because you're subtracting, you're actually going right 2. And then the -4, it's away from the x. It's not inside the absolute value bar, so it does exactly what you expect, which is down 4. And those are all your transformations of that graph. Make sense? Any questions about that? How I got any of that? Because I. All right. So you see here, every single thing kind of does something, right? I have a -3. So if you remember by the graph I have here, that a value, it can both reflect it, right? Reflections over the, oh sorry, the a, right? Reflection over the x-axis, and it can vertically stretch or compress, right? The negative tells you it's a reflection over the x-axis or a vertical reflection, right? Up to down or down to up over the x-axis. Then you have the 3. Well, that 3, it's also part of the a value, which does everything vertically. So it's a vertical stretch by that number 3. And then you have the -2. Because that -2 is right with the x, anything with the x directly is going to do the opposite of what you expect. So you'd think you'd be subtracting 2, but you're really adding 2 to the x's. That's why you're going right 2. And then the minus 4, well, the minus 4 is away from the x, right? It's outside the absolute value bars. Because of that, it will work normally. It's your k value, which goes everything up and down. So it's down 4. Kind of makes sense. Any other questions, guys? Are we okay?
What happens to the F?
The f is just a stand-in for a general equation. So if you have something like f of, or I guess we can call it like something simple, like y equals 3f of x plus 2, like this. The f is just telling you, well, the general function, it can stand for anything. It can stand for like absolute value bars, or like a squared function, or a cubic function, or a square root. It just means it can apply to any of these, or and more. So if I have this right here, and I won't ever ask you this, but kind of to show you an example. If you have this, and then I say, oh, I want this in a square root, right? I'm saying, oh, f is going to be a square root, right? And this is not even really proper math. I'm kind of giving you an example that hopefully makes sense. But we'll say, oh, f is a square root. So you can rewrite this as, well, then y will equal 3. The square root replaces the f of x plus 2. Right? If I say absolute value, you can say, oh, well, then y is 3 times the absolute value of x plus 2. Or if I say the square, y equals 3 times x plus 2 squared. The f just kind of stands for what function you're talking about. Absolute value, square roots, cubic, quadratic, etc.
So that we combine that.
Yes.
Um,
The f would be the absolute value parts in this case. Does that make sense? All right. Any other questions, guys? Are you okay? All right. Let's go on to 2.7. These are the concepts. Make sure you know these. Write them down, whatever you want to do. Does anyone have these written down? Not yet? Okay. Yeah, of course.
the equation earlier when we found H and K, and we had, it was like absolute value of x plus 1. So H was -1.
Yes.
Is it always the opposite, or
Adding, subtracting when it's inside the actual function, the f, yes, it'll be the opposite sign.
where,
Yes. Yeah.
but it's just like 2x plus 1?
When you say 2x plus 1, do you mean like, say, a square root like that? Like absolute values? Oh, like a linear function? Linear functions are really weird because I don't think they even need transformations, to be honest. It's kind of weird because like a linear, the HK doesn't, you don't really have a real HK in this case because it's just a straight line. That's why if you realize from the very beginning, the basic function they had didn't just say here's the parent function of it. It said, well, here's mx plus b, here's y equals x. So I give you 3 different things for the linear function because transformations on it are really, really weird. It's not something I would even think about doing because it's kind of a waste of time. Yeah, because anything with a linear function, you can always just kind of graph it really, really easily, right? You have a slope and a y-intercept, it's very easy. Are we good here, guys? All right. So these are tests for symmetry. You do need to know these. These are kind of confusing, so we're gonna try to. I'm gonna try and make it as simple as possible. So you have 3 types of symmetry. right? It can be symmetric over the y-axis, symmetric over the x-axis, or symmetric over the origin. And what I have bolded is kind of how you prove it with equations. If f of negative x equals f of x, it's going to be reflection. It's going to be symmetric over the y-axis. If it's reflected over the x-axis, it's negative f of x equals f of x. And finally, the last one, symmetric over the origin, if f of negative x equals negative f of x. It's kind of confusing. We're going to do some examples so you can kind of see how it's done. Yeah, young guys? No? Okay. Are we good? Anyone still copying? Okay. Let's do some examples now. So if y equals x cubed, I want to determine whether the graph is symmetric with respect to the x-axis, y-axis, or origin. So we can kind of do it three ways. For the x-axis, remember, I say f of negative x equals f of x. This is kind of not fully true, but it's good enough of an example. Oh, sorry, it's right. A negative f of x equals f of x. Sorry, that one. It's kind of good enough as an example. What that means is that if you have that y equals x cubed, should also be the same thing as negative y equals x cubed. That's what it means. It should be the same thing. And in this case, they're clearly not, right? Y equals x cubed and negative y equals x cubed. Well, that's saying the same thing as y equals negative x cubed. And these are not the same thing, right? Because they're not the same thing, they're not symmetric over x. So for the x-axis, what you do is replace the y with a negative y, and you see, does it give you the same exact function or not? If it does, great, it's a function. It's symmetric over the x-axis. If not, it's not symmetric over that x-axis. Okay? Are you okay with that? Sure, that's fine. So what this means when we say reflection over the x-axis, What that means is you should be able to replace your y value with a negative y value, and you have the same exact function. Okay? As an example, we can go back to Desmos. To kind of show the example we just did right now, what I'm saying, if you have y equals x cubed, like the example we have on the notes right now, I should be able to write a function of negative y equals x cubed, and it should be the same thing. But you see how it's not? The black line is different than the blue line? It's because you see the blue line by itself, it's not symmetric over the x-axis, is it? You know what symmetry means?
It's like it's basically
Yeah, so you can flip it over, it should be on top of each other, right? So if I flip this over, the x-axis, I should be on top of each other. But you see how that's not happening in this regular function, y equals x cubed? That's why it's not symmetric, and when you replace the y with negative y, you don't really have that. Make sense? All right. I think an example of this could be something like, is x equals y squared. This is an example of a symmetric function. If you have x equals y squared, well, x equals negative y squared. You see how it's the same exact thing? Because the original function, the blue one, is actually symmetric over the x-axis. And if you replace the y with a negative y here, you see that? It's the same exact thing. That will be an example of a symmetric. I say function, but it's not really a function. I just think it's the easiest way to kind of talk about it. Any other questions, guys? Basically, with the x-axis, replace the y with a negative y and see, well, do you get the same thing or not? If you do, great. If not, it's not symmetric over x. And now let's check the y-axis. For the y-axis, what we said is that f of negative x should equal f of x. What that means is that I should replace the x with a negative x, and I should get the same thing. So in this case, f of y equals x cubed. So if I replace the x with a negative x cubed, and I simplify this down, I should get the same thing, y equals x cubed, if it's symmetric over the y-axis. Well, y equals negative x all cubed, that's the same thing as y equals negative x cubed. Right, I should have learned. I think y'all dealt with exponents in the other class. If you have negative x cubed, you can cube both those things and take it out. Negative 1 cubed is negative 1, x cubed is just x cubed. So y equals negative x cubed. And this is not the same thing as this function, is it? No, right? It's not. So that's why it's not symmetric. Not symmetric over y. Are we good here? So I want to show, no, did y'all copy that at least? I want to show you all this on Desmos. So y equals x cubed is the function I'm talking about. And you see over the y-axis, the y-axis right here, it's not symmetric, right? If I reflected it over, it's not going to be on top of each other. That's why it's not reflective over the y-axis, or symmetric, sorry, over the y-axis. Because there's no symmetry on the line x equals 0. Are we fine with that? Any questions? Symmetry is very confusing.
Can you show us one that is symmetric so we can see?
Yeah, sure. Y equals x squared. That is symmetric. Right, if I reflected it over the x equals 0, I'll put this too. See the red line is the line of symmetry, the y-axis. If I reflected it over this, it's symmetric, it goes right on top of each other, right? That's what it means to be symmetric. All right. And now I want over the origin. What the origin says is that if you replace the x with a negative, it should equal negative of the original. What that basically means is that we have y equals x cubed, right? Origin can be a little confusing. We're going to go step by step for this one. We have f of negative x should equal negative f of x. Okay? What that means is that f of negative x, I should be able to replace the function, the x with a negative to get negative x cubed. And that should equal the function times a negative, or negative x cubed. Does that make sense? It's confusing, I know. Let me know if does this make sense so I can try to explain it better. How you get rid of the y, I'm guessing? The right here? Oh, here? Oh, I didn't do that. Because this is negative f of x, right? What that means is that the whole function is multiplied by negative. So negative of the function, negative x cubed. Sorry? Because that's what they gave me. So let's do this step by step. So just kind of figure out what's f of negative x. F of negative x, that means you take the function and you replace the x with a negative x, right? So instead of x cubed, it's going to be negative x cubed. We're fine with that? And then negative f of x, that's the function times a negative, so negative x cubed. Are you fine with both of those parts? Are you fine with both those parts right there, guys? Make sense? Well then, from here, just set them equal to each other. So set this equal to this. So negative x cubed equals negative x cubed. I want to see if that's true or not. So remember before, you have negative x all cubed. You can distribute the cube to both of those things to get negative x cubed equals negative x cubed. And that's true. So this is symmetric. Symmetric. I hope I spelled that right. So this case is only symmetric over the origin. Any questions about any of these three? Or this problem right here?
F is negative x.
Okay.
Okay, next step you
No, that's the f of negative x equals negative f of x is the definition. Right here, to tell if it's symmetric over the origin, you use that formula right there. F of negative x equals negative f of x. That's what you're using here. And that's what I'm trying to prove.
so can they get this equal to each other? The symmetries at the top.
What do you mean by that?
So like can f of x just equal to like the origin one, for example?
Yes.
Can f of x still equal to f of negative x? Or it's just
No. So we tried that, didn't we? F of x equals negative f of x. It didn't work.
oh I see. Oh
So I think you're getting kind of because the origin, what it is, being reflection of the origin, what it means is being reflective over the y and x axis at the same time. So you get it?
yeah, I get it now.
Okay. It's a little confusing. Any other questions, guys, before we move on? Because these, I did see this on the final exam review. This will be on the final and the test. All right. Let's keep going then. Now we have y equals x squared plus 5. All right. So in this case, we're going to test all three again. We have the x-axis. Remember, for the x-axis, what that means is negative f of x equals f of x. Again, that's, I should put this in quotations. This is kind of just general. It's not really true, but it's good for our cases. Okay, so negative f of x equals f of x. So I guess what we can do is actually just solve each part by itself and see what we get. So negative f of x, that's going to be taking the function and multiplying the whole thing by negative. So negative of x squared plus 5. Make sense? Or we can say negative f of x is negative x squared minus 5. That's what negative f of x is. Well, now I know, well, what's f of x? Well, I know what f of x is. It's just a regular function, right? So you have two sides of the equation. You just kind of solve for each side by itself, and then see how they're the same. So negative x squared minus 5 is not the same thing as x squared plus 5. So it's not symmetric over the x-axis. Are we good here? Any questions, guys? All right. Because see how we need negative f of x equal f of x, right? See how negative f of x equals negative x squared minus 5, and f of x is x squared plus 5? They're not the same, are they? You need them to be the same thing. So because they're not the same, it's not symmetric. Now the y-axis. For the y-axis, remember that's f of negative x equals f of x. Right, f of negative x equals f of x right there. That's what I want to know. So let's kind of solve each part by itself. Well, what is f of negative x? That means you need to replace the x with a negative x. So you have negative x squared plus 5. And I guess we can actually simplify this down first. Negative x squared is just going to be x squared, right? You can distribute the square to both the negative and the x. Negative 1 squared is just 1. X squared is x squared plus 5. So f of negative x is just x squared plus 5. It's normal. And then f of x, well, that's normal. We're not messing with it. It's just x squared plus 5. These are the same. So it is symmetric over y. Any questions about x and y axis? Are we good? All right, now for the origin. For the origin, remember this needs to be negative f of x equals f of negative x. So to solve for each one individually, so negative f of x, that's negative of the whole thing, x squared plus 5. Or negative x squared minus 5. Then f of negative x will be negative x squared plus 5, which we just saw is just x squared plus 5. So what I have is, well, negative f of x is negative x squared minus 5, and f of negative x is x squared plus 5. These are not the same thing, right? Negative x squared minus 5 is not the same thing as x squared plus 5. So not symmetric over the origin. So in this case, you're only symmetric over the origin only. Oh, sorry, not the origin, the y-axis. Well, we only need to check for up to one because it can only be symmetric over one of them. I just wanted to show you the origin. because we know it's symmetric over the y-axis. Ready to keep going? Any questions? How much more do we have here? 34. Even odd functions. These aren't that bad, actually. So I don't want to sit here and lecture the whole time. I want to give you all time to study because you have your test next, right? Um. Yeah, yeah. 712. How much we have in the other function, other class? We have 9 there. We still have. It's a lot, actually. 3, 4, 5. We'll finish 3 and 4, and then we can end class. How about that? Okay. So, f y equals x minus 2. So I want to know, well, let's check if it's symmetric over the x-axis first. What the heck? All right. So for the x-axis, what that means is, what is it? Negative f of x. Yeah, negative f of x equals f of x. So let's kind of find out what each one is. Negative f of x. That's negative of the whole function. So negative of the absolute value of x minus 2. So negative f of x is negative times the absolute value of x plus 2. And that needs to be the same thing as f of x, which is the absolute value of x minus 2, which is not. Negative times the absolute value of x plus 2 is not the same thing as the absolute value of x minus 2. Or, whoops. Like that. So it's not symmetric over the x. Now let's look at the y-axis. All right, for the y-axis, we need f of negative x to equal f of x. So in this case, f of negative x is the absolute value of negative x minus 2. Well, the absolute value of negative x is just x. And f of x is just absolute value of x minus 2. Everyone with me? So these are the same. So yes, it is symmetric over the, what's it called, over the y-axis. And because this is a function, it's technically a function. Not technically, it is a function. It can only be symmetric over one of these, not all three, not more than one. But there are some cases when you have something that's not a function and it could be symmetric more than one. So we're going to test the origin here just to show you what it'll look like. So the origin In this case, that means negative f of x needs to be equal to negative, or f of negative x. Honestly, for the origin, we already kind of got all that, didn't we? Negative f of x is way over here. So you can just rewrite it that negative f of x is negative times the absolute value of x plus 2. And also f of negative x, we just did that one as well. That's the absolute value of x minus 2. And negative times the absolute value of x plus 2 is not the same thing as the absolute value of x minus 2. Not symmetric. Oops. Over the origin. Are you okay here? Questions, comments, we're good? Ready to keep going? Hang on. Sure. Are we good? Okay. All right. Example 4. This is not a function because it fails the vertical line test. So this is possible to be symmetric over more than just one way. Okay. So let's kind of check all of them again, because we kind of have to for this case. For the x-axis, in this case, we need f. Let's forget this one. F of negative f of x equals f of x. So in this case, what I'm going to do here is I'm going to rewrite this first as, oh, this one's actually kind of ugly. It's not really a function. This is why I don't want to say it this way. Okay, let me do this way. For the x-axis, the more proper way to say it, I don't want to say it this way, is just that any point xy is the same thing as x negative y. All this really means is we're going to do it the same way. We're solving it the same way, just that it's kind of weird to do it this way. All it means is that you replace the y with a negative y. So in this case, x squared plus negative y squared equals 9. This should be the exact same thing as the original. That's what it means to be reflexive over the x-axis. It's the same thing as before. It's just in this problem, it makes more sense to write it this way. Replace the y with a negative y, and you should end up with the same equation. Negative y squared is still just y squared. So in this case, yes, it's the same exact function. It is symmetric over x. Are we fine there? I know I kind of changed the definition. Is that for the other case, it makes more sense to write it that way, when really all it means is for the x-axis is just that if you replace the y with a negative y, you have the same exact thing. That's all it means, like before. We're okay with that? All right. For the y-axis, remember that f of x should equal f of negative x. Again, with the f of x with something like this, the circle, it's kind of weird to think about it this way. Another way to think about it is that x and y should be the same thing as negative xy. Or in other words, I should be able to replace the x with a negative and have the same exact thing as the original. So you replace the x with a negative. Well, negative x squared is just x squared plus y squared equals 9. Well, that is the same thing, so it is symmetric over the x-axis, sorry, the y-axis as well. And now for the origin. So this was negative f of x equals f of negative x. Another way to say this is that the point, not negative y, but the point x negative y should be the same thing as negative xy. Or in other words, just like we did before, for the first case, all this means, replace the y with a negative y. And this needs to be the same thing as if you replace the x with a negative x. Everyone with me here? Because this is not a function, x squared plus y squared equals 9, it's not really a function. It's not a function at all. You have to kind of use a different definition which means the same thing. You still solve the same way we did before. You still have those nice definitions of f of negative x equals f of x or whatever it's going to be. So in this case, x squared, well, negative y squared is still y squared. And negative x all squared is x squared plus y squared equals 9. So they're still the same thing, so it's symmetric over the origin. So in this case, this circle is symmetric over all three. And that will only happen if you have something that's not a function, like in this case, the circle. Any questions, guys? Are we okay? All right, I told y'all we'll end after this. The next two problems are exactly what, well, the next three problems are exactly what we just did, except a little easier. So we'll stop there. Good luck on your test.